excited for this last part of today's conference. This is where we're going to hear from some of our students and their research. I want to thank our colleagues at NYU Tandon for joining us again and for our students saying yes. And then first and mostly, I want to thank my colleague, Rose Ampuero, who's here with us, who is the Associate Dean of Student Affairs and Chief Inclusivity Officer at NYU Tandon that I've known for many, many years and worked together very well over the years. And so just thank you for your coordination. Thank you to the students for saying yes today and for joining us. And I'm going to turn it over to my dear colleague, Rose, who will introduce our students and also frame what we're doing next. Thank you, Rose.
Thank you, Monroe. I'm going to stand on stage because I'm a little vertically challenged. Good afternoon, everyone. It's great to see you all. I'm delighted to see that people are staying till the end. As Monroe said, my name is Rose Ampuero. I'm Associate Dean of Student Life and Chief Inclusivity Officer at NYU Tandon. And I have brought with me today 4 wonderful students that are going to present on their research in the IDBEA space. Their presentations are only 5 minutes long, so I have 4 students with me. And after the presentation is over, you might have a chance to ask them a few questions. So I'm going to go ahead and read their bios. Our first presenter is Nick Hudanich. He is a senior in transportation engineering and a BS MSS student at NYU Tandon, specializing in transit mobility and traffic engineering. He is a researcher at the C2 Smart Transportation Research Center and has pioneered projects such as the J Street Accessibility Station Lab and the COVID-19 Data Dashboard and White Paper series there. Nick is president of NYU's Institute of Transportation Engineers, or ITE, student chapter, and led the team to 2nd place finish at the International ITE Traffic Bowl earlier this year. Nick is an organizer of Transportation Camp NYC and an active member of the Young Professionals in Transportation Society. Our second presenter is Bingqing Liu, who is a 4th-year PhD student in the Department of Civil and Urban Engineering, focusing on transportation. Bingqing's area of focus is networking, modeling, optimization, and operation research regarding shared mobility and multimodal transportation systems. Our third presenter is Fabiana Ricci, receiving a Bachelor of Science degree in Mechanical Engineering from Sapienza University of Rome in 2019 and a Master of Science degree in Mechanical Engineering from NYU Tandon. She is currently a PhD candidate in Biomedical Engineering, and she is involved in research, rehabilitation, and human-computer interaction. Our fourth and final presenter is Miao Zhang, who is a 2nd-year PhD student majoring in computer science and engineering at NYU Tandon. Zhang's research is about model fairness in visual deep learning, focusing on environmental and healthcare-related data. Zhang is currently looking into model prediction disparity across geographical places in real-world practices and has general passion in human-centric studies for social good. Please welcome our students.
All right, hello everyone, I'm Nick Hudanich and I'm from C2 Smart Center in Tandon. I'm a BSMS student in Transportation Engineering, and today I'm going to talk about one of the technologies that we've researched over the past few years. There we go. So over the past 15 years, one of the hallmark goals and achievements of New York City is to achieve Vision Zero. There are still 40,000 plus crashes and collisions in the city every single year. And of those, 20% are pedestrians, 1/4 of which are at intersections. Intersections are one of the most dangerous places for cyclists and pedestrians in the entirety of the city. And over a series of funding projects, the US DOT has said we want to address these issues and develop programs and new technologies to reduce the number of fatalities. And the gold standard of this is V2X, which is basically an environment where the vehicles will communicate with infrastructure and the infrastructure will communicate with pedestrians. And it's a form of data flow that it can even inform cars to swerve away from collisions or mitigate their speed. And there's all these different technologies, thousands of them emerging. And part of our role under a contract with the US DOT is to evaluate some of these and determine their merits and shortcomings. Specifically, there are 3 connected vehicle pilots that USDOT has employed. One of them is in New York City, which we are pioneering. And specifically in New York City, they've deployed 3,000 cars, which are equipped with onboard units, which are basically data transmitters that can collect and receive data, inform the movements of the car, and tell the infrastructure where the car is in space in order to send alerts to pedestrians or cyclists, or do some function to protect the safety of one or more parties. The other direction, it can control the vehicle's speed and trajectory and keep it on a path that prevents it from colliding or stopping if there's a red light, those sort of mitigation methods. So specifically, the technology I'm going to be talking about today is called the PED-SIG app, and it's not a panacea for intersection navigation problems, but it is a help and a tool to try to ease the confusion and increase the navigability of intersections. So basically, the PED-SIG is an app that you can hold on your phone, and as you are approaching an intersection, it will tell you your orientation in space, where the sidewalk is, and what the indication on the signal is, whether it's okay to cross or not. And the real genius behind the app is it won't just give you the indication if you're any direction. It will only give you the appropriate directions if you're exactly lined up with the crosswalk. This prevents drift either into the intersection or into the block. And by the timing countdown, it will tell you only when it's safe to walk. It won't tell you it's safe to walk if it's counting down with 5 seconds left to cross. It will only tell you it's okay to cross if there's sufficient time for you to get across the intersection. And it will give you guidance on where you are in space, crossing Hoyt Street West or Bond Street North. So it's meant as a tool to ease the confusion. Where am I in the intersection? Where's the crosswalk? Is it safe to cross? And so our role at CGSmart was evaluate the software and determine whether it was useful or beneficial, and if not, what shortcomings did it have? What needs to be addressed in the future to make this a viable app? And the primary method which we did this was surveys followed in tangent with field visits. So we recruited 14 different participants who had varying levels of visual disabilities, and we had them we gave them their own phone. Ideally in the deployment, it would have user's own phone, but we had our own custom phones where the users would, it collected data beyond what we were asking them, but the users would try to navigate. We'd try to minimally influence their movements in the intersection, and then we'd survey them on, did it make you feel safe? Did it give good information? What was the level of responsivity of the app? Those kinds of measures. And it was overwhelmingly positive from all the participants. No one said that the app had any negative effects. There was a small percentage, about 20% of neutral effects, and 80% were split between it was extremely helpful and slightly helpful. And the most important metric in our regard is safety. A large majority, 83% of people, felt that it increased safety at least somewhat in crossing intersections and navigating. The shortcomings that we discovered through the deployment of the software was that it relies a lot on the GPS data of cell phones, and cell phones in themselves are not typically accurate right now. They're 30 feet or so in their range. So we actually had to equip a separate GPS device connected to the phone to transmit a more accurate location down to 5 or 6 feet. That's a limitation of phone technology. So as of now, you would need a separate GPS device equipped with the technology. In the future, hopefully GPS technology can get a little bit better. Part of that is because we're in New York City and there's a lot of interference from different radio waves and electromagnetic waves. There's not a lot of interoperability with the app right now. Ideally, as I mentioned, this is not a panacea. It's a tool to be used in conjunction with other means, and having some sort of way to integrate this with apps such as NaviLens or other mobility apps would be ideal. And I think that is it. Thank you.
Okay. Hi, everyone. My name is Bingqing, and today I'm here to introduce our work about a zone design algorithm for equitable data. I'm working on this with my colleague, Farnoosh Dabber, and our supervisor, Professor Joseph Chow, and we're also from the City Smart Center, same as Nicholas. Okay, so let's get started. So if you have dealt with a spatial data, you will know that spatial data is always based on zoning systems. So for example, for smaller ones, we have, oh, it's not moving. I'm having like some animations here. Maybe I'll just go on. So we have like smaller ones like the census box, can see that it's very small, and we can have larger ones like the census tracts, slightly larger, and we also have like the Puma zones, which is much larger, and we also have the growths. So you lose all the details. So it's obvious that if you look at the same data with different zoning system, you get very different results. So if you look at the distribution of the seniors in New York City, if you look at them at the growth level, you only see the aggregated data. But if you look at that, I'm sorry, it's skipping my slide. But if you look at that at the census tract level, you will see very detailed distribution. You will see where are the seniors actually at in the city. So yeah, so that's why we want detailed data. But let's look at how reliable are these like detailed data, like very small zoning level. So we looked at this census tract, which is at Midtown Manhattan. We look at the population data of different age groups. You can see that the last column is the error percentage of the data. So you can see that the smaller the group is, the more unreliable the data is. Okay, so what we discover is that the data of the smaller groups tends to be less reliable. So we also checked that for all the other minority groups. So we found that as a very common phenomenon for the minority groups, that their data is much less reliable than the majority groups. So the reason is the small sample size. So we have very small sample size for these census data. So the coverage of the minority groups is even poorer than the majority groups. So what we're doing here is we want to aggregate small zones into larger ones to have larger sample sizes for within a single zone, so we can achieve more reliable estimates within those zones. Okay, so for example, if we look at these 3 census tracts at Lower Manhattan, and we look at the population below poverty level at these zones, that's at the non-reliability levels. So, however, if we combine them together, the non-reliability level becomes much lower. But however, we cannot just randomly combine zones together. For example, if we combine these zones, somehow we can lose the pattern entirely. But even if we combine the zones like into the same number of zones, different combination patterns can lead to very different statistical results. So that's why the zone design matters. So what we did is we designed a zoning algorithm that can aggregate the zones properly for a data of a certain minority or several minority groups together. So finally, we arrived at the NYC equitable zoning for the seniors, the low-incomers, and non-commuters. So you can see that their data reliability is significantly improved. So what you might not expect is that such kind of zoning algorithm can also help with data sharing. So because we have different mobility providers and also other like privately owned public service providers, and they need to be managed by the public agencies. So they need to share data with each other. However, this can be less efficient if they don't have like a data sharing digital infrastructure. So if we have that, they can use that to do the data sharing. So that actually already exists because the mobility data specification is such a digital infrastructure that has been applied for a lot of cities and states in the United States. And I believe New York City is also seeking to have something like that. And however, not everybody is happy about it because people are concerned with data privacy issues, and Uber already sued them in LA. So yeah, how the zoning algorithm is going to help it is that we aggregate the data into zonal level. So that resolves privacy concerns. So now we are seeking to work with MDS, have an updated version of mobility data specification that is able to output different zoning systems. So the government, the mobility providers, and users can sit together and look at this zoning system to find a way of data sharing that everybody is happy about. Okay, so sorry for the I misused the clicker. So yeah, let's pass to the next.
Hi everyone, my name is Fabiana Sofia and I'm a PhD candidate in biomedical engineering and I work in the Dynamical System Laboratory directed by Professor Maurizio Porfiri. My research focuses on developing a virtual and augmented reality platform for helping people that have visual impairment regain their mobility. And this project that we did this summer with undergraduate students is about inclusive design for persons that have a visual impairment. So as a general definition of inclusive design, for inclusive design is meant any kind of design of services and products that can be accessible to anyone independently of their impairment or their abilities, without the need of special adaptations or design. So in our case, we focused on the indoor environment because the inclusive design can be applied to different fields. So from the design of devices, of web pages, to indoor and outdoor environment. So in our case, we focused on developing an indoor environment which wants to resemble our academic environment at CASP, so at 3070 J Street. And so we focused on learning and studying the inclusive design rules and regulation, and we tried to implement these rules in the virtual environment. We focus on some specific guidelines like increasing the contrast at the scene edge, or also adding all the other tips that are usually implemented when you are doing an indoor environment. So now I want to show you this video that was made by the undergraduate students that I mentored during this summer, which is, I think, representative of the work we have done.
Disability, eyesight, and accessibility. Hi, I'm Lavia. And I am Joanna. We worked on a research project, Accessibility for Everyone, Inclusive Design for Persons with Visual Impairment. What is visual impairment? Visual impairment refers to any degree of vision loss that affects a person's ability to perform the usual activities of daily life. According to the World Health Organization, at least 2.2 billion people across the world live with visual impairment. This number is expected to increase due to populations aging, lack of public health advocacy, and poor community outreach. Therefore, developing new technology is necessary to help persons with visual impairment regain their independence and mobility. Persons with visual impairment may encounter various difficulties and harms while navigating most of the current environments. To protect the fundamental rights of people with disabilities, inclusive design theory can be applied to design environments that are more accessible and free of barriers. Thus, we aim to assess how the application of inclusive design principles on an environment impacts the mobility of persons with visual impairment. Specifically, inclusive design regulations we would like to test include identifying barriers that make environments inaccessible or exclude, analyzing navigation challenges, recognizing potential prejudice, creating ways to include all. Finally, extending the solution to everyone despite their disabilities. To create or control an experimental environment, we utilize Unity, a cross-platform game engine which allows for developing virtual reality platforms. The chosen control environment resembles the 12th and 13th floor of 370 J Street, an academic building of NYU Tandon. Here are some side-by-side comparisons between the chosen actual environment and one reconstructed in virtual reality. To make the virtual environment as realistic as possible, we add rendering effects, animations to allow interaction with objects and sounds. After creating the existing environment, we built the experimental environment according to the inclusive design guidelines, laws, and regulations stated in research papers we have reviewed. These measures include having contrasting colors between objects and the walls, removing glass or transparent barriers, and having different materials for certain pavements. With rendering effects available in Unity,
We then simulated a visual impairment on virtual reality to Oculus Plus to allow sighted subjects to experience how the environments may appear to those who suffer from them.
As of now, we don't have results in mobility performance of subjects navigating the two environments, as we are still testing and improving the platform to create the most valuable experience. However, in the literature review that we did, we found a lot of data that confirms what we expect to achieve during our experimental phase.
We hope our findings contribute to furthering development and improvement of aids for persons with visual impairment. We also hope our experimental results may be an incentive for the implementation of legislation on the application of inclusive design in real environments. We must support and help those who suffer from revolution. And so, we must recognize this data and enforce the necessary changes for broader accessibility.
So that's our work, and thank you.
Hi, everyone. I'm Miao. I'm presenting this work with the instruction of my supervisor, Professor Rumi Chinara. I want to talk about the landscape diversity and how that could cause model fairness issue. The first thing to highlight is that even for a same geographic domain, like a city, there could be high heterogeneity across different spatial units. For example, the street views of different counties or boroughs across New York City is very different. I'm gonna show more examples later. And however, even if it's the case, most satellite image recognition tasks have been mostly focusing on the city level or even larger a country level. And it's very easy to ignore the difference between neighborhoods and the groups of populations related to that area. It really skips. Yeah, here it is. Yeah, so we call those groups as sensitive groups or protected groups. And here is an example of sensitive groups being rural and urban. These are two satellite images from a same city, but one from a rural district and one from urban district. And we performed the deep learning model here to do the land cover object segmentation. And you can see from the prediction, the building detection marked in red color. The urban image model segments the buildings very well, but for the rural buildings, model barely detect any of them. So we noticed this performance disparity of our model, which is kind of the initial motivation of the work. So here's a world map of the majority urban and majority rural. So it can be seen in the most places, the population are majority urban. So this is also highlights the need to be careful that we don't get the minority groups underrepresented. There's a detection result example. You can see the circle in blue here. So the urban pattern of the road is also well detected, like in yellow color, but the sand road, which is a common pattern in rural area, is very hard to detect. Yeah, another example of urban rural pattern with the landmark on it. So this is kind of a signal for the model, and it's like a easy pattern. Yeah, this is a more statistical plot showing the land cover composition of these two groups. And you can see from the plot on the left that in the urban area, there are more buildings and roads. And in rural areas, there are more forests and agricultural lands. So yeah, there's a high heterogeneity there. So These are the metrics we use. Maybe we don't need to dive into it, but basically we measure the accuracy of the model as well as the 3 fairness metrics, the standard deviation, a measure of the difference between groups, and also the worst performing groups. We want to say which group has the worst performance across classes and which needs to be improved, and also the top and the bottom performers. So there are 2 tasks we do regarding the satellite images. The first one is on a single domain, which is the single city, and we compare the 2 groups' performance. And it seems the urban get better accuracy results, and rural get better fairness results. And secondly, we perform the domain adaptation, the transfer learning task. A little bit more context here. So sometimes we don't get enough data in one place. So we need to transfer the model trained in one place to another place with like a little data. So there's a commonly used strategy called domain adaptation, which helps the model to adapt to the new environment. And we examined this kind of methods and found that the domain adaptation methods, even though get the model like more accuracy, but get the gap between rural and urban even larger. So that's a risks and it needs to be tackled. Those kind of concludes my presentation. So we want to use the findings here to disclose this fairness issue with geographic data and kind of encourage further investigation and optimizations. Thank you.
So thank you to our NYU Tandon students. Wow, the brilliance, like I understood about 60% of what you were talking about. That's how brilliant you are. So thank you so much for bringing in all of your research projects, and I just wishing you the best of luck as you continue your pursuits, and also for those who are advising undergraduate students as well. Thank you for your contributions. Just really fantastic, and leveraging your education to make a strong impact in the world. We appreciate you. Thank you, Rose, for partnering with us on the lightning sessions as well. Again,